Okay, so we're going into the VSEPR theory and the crystalline solids, right? The last section of topic two that we need to really cover, right? And then that will be the end of it, right? And then we probably move into redox reactions and energetics, and just complete everything with kinetic theory and then into the rates of reactions, right? Looking at log graphs and those type of stuff, right? So let's get into this, right? Before we understand how to really construct these VSEPR structures and understand molecular geometries for covalently bonded compounds, all right, we're going to need to remember Lewis dot structures, how we construct Lewis dot structures, how they generally look, right? So it is a form of chemical representation, right? So when I speak about chemical representation, we know that we can represent chemicals as general formulae, molecular formulae, skeletal formula, right? There are different ways to construct molecules. Now, the Lewis structures, right, are the best way to show the atoms that participate within bonding in the molecule, right? And understanding where free and bonded electrons are and how many free or bonded electrons are in the structures. That is important. Let me just see somebody sent something in the chat. Oh, okay. Let me just accept that. All right, so it's really important that we really look at it. So we need to understand how these structures really look, what's going on with them, and then get into examining our VSEPR structures. The main reason why we really use it is because it tells us what participates, how many atoms participate, how many electrons participate. That's the best way to define our VSEPR structures. All right, so let's really look at it. So the Lewis electron dot formulae, right? So it's a little bit interesting, right? It's not really difficult, but we generally have 5 steps that I would like to look at. All right. The information on the slides are for you guys to like read when you have the PowerPoint or if you want to skim through it. Right. But I'm just gonna go through it, right? So step one, the first thing that we do when we're writing our chemical formulas, right? Write down the chemical element at the center of the structure. No, in Unit 1 chemistry, we tend to deal with really simple structures. Therefore, most likely you're going to always have a central atom. All right, so your central atom is what you draw first. So if I am going to draw something like, hopefully I don't use one of the examples that are in the PowerPoint, because I don't remember what it was in the PowerPoint, but let's use carbon. All right, we're drawing methane. All right, so the first step is just draw that atom of carbon there. All right, sitting there. Then the next step is to count the total number of valence electrons for all atoms in the molecule, or ion, right? So we're generally going to be counting all of these things. So let's say that we're doing methane. We know that we have 1 carbon. We know that we have 4 hydrogens, right? How many electrons would be participating there? How many valence electrons does carbon normally have? This is where somebody jumps up and says the answer because it's so easy.
Carbon has 4 valence electrons.
Wonderful, right? So carbon has 4 valence electrons. Therefore, we're gonna be noting that. So the number of electrons from carbon, we have 4, right? So 4 valence electrons so far. How many valence electrons does hydrogen have?
Hydrogen has 1.
1, right? And we have 4 atoms of hydrogen. Therefore, we're gonna have 4. So we're gonna have overall 8 electrons. Now, that is important because we need to account for every single electron that is present. Right? For something simple like methane, we're gonna notice that all the electrons eventually become eventually identify with a bond. Right? But for structures like ammonia, right, it may be a little bit different where you have lone pairs. Right? So what you're going to do now is connect the atoms in the molecule or ion using single lines, and that represents sigma bonds, right, to represent these covalent bonds. And each line would represent a pair of electrons, right? That's generally it. So I have four hydrogen atoms. So I know that carbon has a tetravalency aspect, right? Tetra meaning four, so it has four valence electrons, right? So what's generally going to happen is that I can note that my carbon has four electrons around it like that. And I note that I have four atoms of hydrogen, meaning that each hydrogen also has an electron. And our structure is going to be looking like this, right? Our end product is going to be forming these, you know, pairs of electrons into bonds, right? So we're going to initially just, we're going to eventually, write them like this. Step 4 is to place dots around the chemical element for each atom to represent the remaining valence electrons, right? And make sure that each atom has a complete octet. That is kind of, well, when we start looking at the fact that some elements have an extended octet and some elements are pretty fine without filling that, well, fulfilling that, octet rule, then we can look at that, especially with, something like sulfur heptafluoride or something like boron trifluoride, right? They're going to be a little bit different. So you're going to have to know those things that don't follow the octet rule, right? So we're going to have something like this, and we need to account for each and every electron, right? Now we know that each single bond counts for two electrons, and we have four single bonds in this compound. Therefore, we have accounted for all the eight electrons, right? The next thing that we should do is represent everything in pairs of electrons if we have any free electrons outstanding. On this molecule, we don't have any free electrons outstanding, right? If the structure has a formal charge, add or remove electrons to balance the charges on the atoms, right? So formal charge. I'm not sure if anybody knows what that is. Can anybody tell me what formal charge is? What is the formal charge of an atom or ion? Go ahead.
It's the number of valence electrons in the neutral atom minus the number of bonding electrons. It's half the number of bonding electrons minus the number of non-bonding electrons.
Okay. So we're going to be looking at that. So the formal charge of a molecule tends to, well, of atoms tend to be equal to, as you were saying, the valence shell, the amount of electrons on the valence shell, minus the number of non-bonding valence electrons, right? And that would be minus the amount of bonding electrons halved, right? Let me just quickly get this in there, right? Oop. So you're going to have something like this. It's going to be equal to valence electrons. I don't want it to look like electron volts, so I'll just use V, right, for valence electrons minus the number of non-bonding electrons. So N non-bonding electrons, right, minus bonding electrons divided by 2. All right. So if that comes up to be somewhere, above or below zero, we try to rearrange it to make sure that it has at least the least formal charge. Now, some molecules have to have a formal charge because some of them are ions, right? So some of them are a bit different, right? But in those cases, the structure with the lowest formal charge, which will be said to be the most stable structure, and the one with the highest formal charge, right, is the most unstable, right? So that's generally what we're working on, right? So let's have a look at something like this, right? This is generally the first two steps. We look at our central atoms specifically, so we represent atoms themselves, and we place the number of valence electrons around the atoms, variously like that. So this is our representation of oxygen and nitrogen as examples, right? So that is generally how we come up with the structure, right? I put this extra information here as another tool of explaining how it works, right? Because there are two general ways, right? The way that I used here, which are just quick 5 steps, but sometimes persons need a little bit more details as it relates to connecting the bonds and making sure there's a full octet and stuff like that. So there's more information here, as well as how to calculate the formal charge on a molecule, all right? And this is more in depth because now we are talking about the stability of a molecule generally, all right? But we're gonna get through this. Should be fine. Are there any questions though? Any questions or concerns? So if everything is fine so far, just drop a one in the chat, please. Just drop a digit, a number one in the chat. And if there are any questions, you just unmute and you just let me know. Even if it's a comment, you can just let me know the comment, by the way. Give me a moment, let me just verify something on this slide. That would be that. So that's over that. So that would be. All right, so the information is right because that structure is fine. Okay, so that is it. I have to really verify this information because I no longer draw structures with the rules. When you understand the rules and you internalize the rules, you just draw any structure, right? So it just comes with a little bit of practice. Now, the Lewis structure for N2, right? So this is the information or the tools to draw the Lewis structure for N2. So I want you guys to just go ahead and draw the Lewis structure for N2 real quickly. Should take a couple seconds, at least at most 30 seconds, right? Just let me know when you're done. Just drop a one in the chat when you're done with the Lewis structure for the nitrogen molecule, please. All right, so the information is already on the screen. It's constructed. Just let me know when you're done. Because even though you may already conceptualize and understand how to draw the thing, when you draw it's a little bit easier to complete other structures. Go ahead.
Sir, some people want to be let in.
Okay, let me just check. Thank you for letting me know. Ooh, all right. Okay, that's a lot of people. All right, so go ahead. Are you guys finished with the N2 structure? Yes, no, maybe.
Good afternoon.
Good afternoon.
Should we write this down?
No, no, no. You're going to
Oh,
receive the PowerPoint.
I thought we were starting 6, that's why I'm late.
Oh, that's fine. Okay, I'm not seeing anybody replying about the structure. All right, so we're just going to continue then. All right, so the nitrogen gas structure tends to form this bond. All right. Now, before I continue, there are some best practices that I would like you guys to use. I know that you guys understand that electrons repel each other. Fine, fair enough. All right. So if you're going to be constructing nitrogen like this, please don't leave your electrons like that. That's not it. Right? Don't leave your electrons in awkward positions. Right? We try to make sure that they're completely understandable and agreeable, right? Electrons repel each other, therefore they will be at the farthest poles away from each other. All right, so try to represent that best. Right? The more we draw Lewis structures and realize that electrons repel each other, that's going to be a wonderful assistance in the valence shell electron repulsion theory. All right, so some best practices there. We're going to be moving on. All right, so the structure of CO2. All right. Um. Okay, so let's just do the structure of CO2. So we're saying that we're gonna have one carbon atom, right? In the center, one carbon atom, and it has valence electrons around it, four valence electrons, right? And then it is flanked by two oxygen atoms, right? So we have one, two oxygen atoms, right? Oxygen has how many valence electrons?
6.
That's a question, by the way. How many valence electrons does oxygen have?
6.
6.
All right, tough crowd. Um, I don't know. All right, so looking at something like this, oxygen has six valence electrons. Therefore, we're going to be constructing that around it. So one, two, three, four, five, six. Right? So one, two, three, four, five, six. So six valence electrons around oxygen. Right? So that's what we're gonna do first. Then we're going to try to draw bonds, right, to make sure that your central atom has fulfilled the octet rule thus far. All right? And we have to share them. So since each oxygen atom would require two electrons to fulfill noble gas configuration, and carbon will require four bonds to fulfill noble gas configuration, we can just express that like this, right? Oxygen has its shared electrons now. Carbon has its four bonds, and everything looks fine, right? So this is general structure that we have for CO2, right? A doubly bonded compound, right? And if anybody can just generally recall, all right, what's happening here. Let me not go into that actually. Let me not describe that actually. So let's just continue with this. So that's generally Lewis structure for oxygen, right? And then here now we have something a bit more complex, right? The carbonate ion, right? So I want you guys to actually try the carbonate ion CO3 2 negative. So it's CO3, and we know that the charge on it is 2 negative. I want somebody to try it, right? So I won't continue because nobody answered. So I want you guys to actually try this one. And after we're done trying, then we may move on. So let me know when you're done with it. I'm going to go back to the rules so you guys can look at the rules to have a general understanding of how we draw the structures. So try CO3 2 negative. It's a really complex, well, it's a complex one. Right, so I'm going to just allow you guys to do that. When you're done, let me know. If there are any questions, you guys can ask as well. Let's draw the structure, let me know. Let me participate in the structure. That's wrong. Mm. 1, 2, 3, 4, 5, 6, 7, 8. That's done. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. My structure is finished. It's gonna be negative, negative. All right. Just let me know when you're finished with your structure. All right. So Anna is done. Anybody else completed? So see, Anna is the first person. These tasks of completing Louis structures generally take, or should generally take us 30 seconds. Right? So when we practice them and go through them, then at max, if it take you more than 30 seconds, then we'll get straight back into the understanding the rules and practicing. But it shouldn't take more than that. If it does, then just more practice. Anybody else completed with structure, or we just move on with Anna alone? All right, finished. So Sean is finished. Oh, sorry. Sean is finished. Sean, Sean, yeah. All right, so seems like majority of you guys are done. A good amount of you guys are done either because that's not the majority. But let's have a look at our carbonates, right? So let me just look at the structure first. That is the structure of carbonate, right? So it is a polyatomic ion, right? So we generally have this structure. So the first thing we do, we know we put our carbon down, we put our oxygens with the valence electrons, and then we try to connect using bonds, right? So we create bonds using two valence electrons, right, of the negatively charged oxygen, right, and then we use around we'll connect that with one bond, right, and then we're going to use double bonds for one of the carbon atoms, right. This will actually give us complete octets, right, for everything in the compound so far, right. And then we're going to have a negative charge on two of the oxygen atoms because there are actually arranged lone pairs that increase the charge on the oxygen atom, right? And it's also based off of the formal charge. So if you have any issues with the molecule itself, right, I suggest that you go back to the rules, redraw it, calculate your formal charges, make sure that the formal charge on the entire molecule must be 2 negative, right? On this structure here, oxygen is fine like this, right? Oxygen is generally fine with two lone pairs. And by the way, there are anomalies. Once you practice, you're going to be able to remember all the anomalies, right? So oxygen is fine with two lone pairs. Perfectly okay, right? So what generally happens here now, oxygen only has one bond in this structure here. One bond. Let me just use this, right? One bond in both of these structures, right? It allows it to have an extra lone pair, concentrating extra charge. So the formal charge on these oxygens will be -1, right? We said that the formal charge is valence electrons minus non-bonding electrons minus bonding electrons divided by 2, right? So if we look at it like that, the valence electrons on oxygen, right? We're going to have generally 6 valence electrons for oxygen minus the non-bonding electrons, 1, 2, 3, 4, 5, 6, right? And we're going to be minusing, right, the bonding electron, which is 1 over, which is 2 over 1, actually, right? Well, 2 over 2. Sorry about that. I'm lapsing, right? So the sixes we cancel. We're going to end up with -1 there, right? So we're gonna have 6 minus 6 is 0, minus 1, 1, minus 1, right? So we're gonna have a negative charge on these oxygen atoms, right? And if we're gonna have two negative charges, we can bracket the entire ion, right? And put two negative on it like that, all right? So two negative, that is it. Everybody's fine with that? Want in the chat if everything's fine so far, and we can move on. All right. Wonderful. Okay. So understanding this is just what we need to do. So a recap of the way start structures, and then we head into the the VSEPR theory. All right. So the VSEPR theory, or the VSEPR theory, the valence shell electron pair repulsion theory, is a basic theory that we use to predict the structure of well, the geometry of covalent compounds, right? You could say the structure as well. It's all based off of molecular interactions or electronic interactions with atomic species, or we could just say lone pair interactions, bond pair interactions, right? So we generally look at the repulsion of electrons, and in this case, we normally look at the fact that electrons are negatively charged, so they're gonna try to find the best way to always, be a furthest apart from each other, right? As well as bonded species, right? If we have multiple atoms around a central atom, they're going to actually spread apart, right, to make sure that they're at the maximum distance apart, right? So that's the main understanding of the VSEPR theory and what we need to really get through, right? So we have some postulates here, some really important postulates. Right, so the first one, I'm going to be going through all of them verbatim off of the slide, by the way. So the first one, all the electron pairs in the molecule are arranged in such a way that they minimize the repulsion between the electron pairs of the atom. Right, so they spread out furthest distance apart. That's basically what the first one is talking about. The second one is that the central atom of a polyatomic atom, right, of the polyatomic atom, right, is the well, would should be a molecule, right, is the atom to which all the other atoms of the molecule are linked, right? So it's generally something like that. So some things can be binary, some molecules can contain the same atom specifically, right? And some can contain different atoms, right? Because some elements tend to be able to bond to each other, right? The same element, for example, carbon-carbon chains, right? So in a species where you have a different central atom from all other bonded atoms, right? We're really looking at this, right? It's a little bit detailed, but yeah. Valence shell electrons of the molecule are responsible for the shape of the molecule, right? That's what we're looking at. The valence shell of the molecules is arranged in such a way distance is maximum, right? And therefore repulsion is minimum, right? So a lot of these things kind of drive home the points, in a sense, right? If the central atom of the molecule is surrounded by bonding pairs, right, then the asymmetrically shaped molecule is formed, right? So we're gonna have an asymmetrically shaped molecule, and we're gonna look at how that works, right? And why is it asymmetric? Right? Then if the central atom of the molecule is surrounded by lone pairs and bonded pair electrons, then the shape of the molecule that is formed is distorted. And we're gonna look at molecular distortion or geometric distortion, right? Then in each resonance state of the molecule, we're gonna be experiencing resonance states and stuff like that a little bit sooner than expected. All right, but it's really used for unit 2, right? And then the force of repulsion between the lone pairs, right? So lone pair, and bonded pair follows that order, right? No, this is a lot of information, right? It's there to read, but I'm just going to guide you through it now, right? This is the order in which the repulsion follows, right? If you have a lone pair of electrons repelling a lone pair of electrons, that is the strongest interaction, all right? If we have a lone pair of electrons repelling a bonded pair of electrons using the line to represent a bonded pair of electrons, right? Then that is weaker than lone pair interaction. And then the weakest interaction is bond pair interaction with bond pair interactions, right? So you can see some of the examples here, and we're gonna explain in each structure why we tend to get these geometries, right? So before I move on and completely explain what this has to do with molecular shape, is everybody following thus far?
Yes,
Any
but the
questions
diagram
so
doesn't
far?
make sense to me. The diagram
All
there
right, I'm
doesn't
not
really.
hearing any questions.
Hello?
Just a reminder that you can always ask a question at any time. Then you can always
Can
stop
you
me in
hear
the middle
me?
of speaking and
Can you
ask a
hear me?
question. All right.
Oh my.
But yeah, so let me completely explain this now. All right. We're gonna be using it to predict the shape of molecules. All right. But I'm going to get into the shape of molecules so I can explain how. Oh, someone was speaking. I apologize. Can you go ahead, please? My apologies.
Can you hear me now?
Yeah, I can hear you now.
Oh my gosh. Because I was speaking earlier and I was like, are you ignoring me or something?
No,
It's
no,
okay.
no.
Um, the diagram there doesn't really make sense. I don't understand it.
Okay, the diagram does make sense. All right. So let's use the diagram then. So, okay, let me just ask one more question. What about the diagram doesn't make sense?
It looks foreign. The second part with the brackets around it.
Okay, so the second one will back it around it. All right. So what we're seeing, let's look at water. All right. This is wrong, by the way. Definitely. So I'm just looking at diagram properly and realizing that that's not good. All right. So let me see if I can. Give me one moment, please. I can hear that at the exact same time I'm hearing them. So if I turn this off, I can't hear them. Yeah, I can't hear them when I turn the left one down. I'm explaining that to you right now. Yeah, so I'm not hear anything. Hello? You still in on the game? But if you turn on the master volume, that'll turn on everything coming. Alright, moving on. It'll turn on everything so you don't need to turn down everything. Okay. Alright. Sorry about that. Alright, so let's continue like this. So let's look at a water molecule. Alright. So the water molecule generally, if we have the Lewis structure, let me do it on a completely different page. So I make sure that this makes sense. I'm gonna be a little bit late for unit 2. Alright. Alright. So let's draw water, right? Oxygen is a central atom. Oxygen has one, two, three, four, five, six valence electrons. Then we're gonna have hydrogen. Let me draw it like this. Hydrogen here. Hydrogen is gonna want to bond, right, with one of these electrons. So let's say that it bonds with this electron here, forms a bond like that. All right. So what we're gonna end up with is bond like this, and we're gonna end up with valence shells like this. Well, valence electrons like this. Make sense so far?
No, can do that again, please.
Okay. All right. So let's start out. Right. So when we draw our central atom, right. So first thing we do is draw the central atom, right? Oxygen, and we display it with its valence electrons. Oxygen is in group 16, therefore it has 6 valence electrons, right? So just going to draw some valence electrons around the oxygen. Following?
Yeah.
All right. So in water, water is H2O, right? So oxygen dihydride, right? So we're gonna have this like that. We have two hydrogen atoms, right? So let's just display the two hydrogen atoms somewhere around the oxygen. And each hydrogen atom has one electron to share in covalent bonding. All right. Now, what the first thing we're going to do, we're gonna use single bonds. right? We're gonna be using single bonds to connect the atoms together, and then after that, then any type of opening for double bonds or triple bonds, then we add them in. But so far, we're gonna try to connect everything in the compound or the molecule. Well, this gets the compound. Anything in the compound with a single bond, right? So we know that all of them need to be bonded together. So we're gonna start with using single bonds. So I'm just drawing this around these electrons just to say I'm choosing that electron on oxygen to just, bond with, right? So we're gonna make bonds out of these. And when electrons are shared, we're gonna have single bond like that. We're gonna have these electrons left over. Make sense? Because 1, 2, 3, 4 is not bonded.
Yeah, it makes sense, but I thought they were supposed to be like at the maximum distance possible. So
Oh, we're getting
I
there.
expect like the O in the center and the H them like west east.
Okay, hold on. This is what you're expecting. All right, so I understand. All right, but give us one moment. Now, to understand how we even get this weird structure of water, right? Geometry of water, right? We have to use the VSEPR theory. Now, the valence shell electrons here and here has high repulsions with the bonds, right? But yet again, we have to actually look at the molecule itself in a 3D structure, all right? So what's gonna happen here is that the electron, the bond pair, electron pair or lone pair interaction is going to be extremely strong. So what generally happens in water or molecules that have this general structure, the electrons are going to migrate to form something similar looking to this. All right, let me not bend that yet. All right. So one electron sphere of influence is going to be there, one electron sphere of influence is going to be there. They're going to be repelling each other, so they're at that specific angle, right? Now, we can't have this in a linear arrangement because we're going to have electrons repelling the electrons in these bonds. We're going to have lone pair, bond pair repulsion, right? And that's going to bend the water molecule into the structure that we normally see it in. All right, I'm going to clear up here, right, and clear this so you can see what's happening, right? So the electron pairs are here, 1, 2 electron pairs, lone pairs, right? And when it bends it, it's going to move these bonds to migrate at a specific angle, right? So we're going to end up with the lone pairs at this angle here and the bonded pairs at this angle. Right? So the bonded pairs and the lone pairs repel each other, and since lone pair interaction is stronger than bonded pair interaction, the bonded pairs would be, brought closer to each other more so than the lone pairs, right? Because we did state that lone pair interaction is the strongest of all interactions, right? Then we tend to have lone pair bond pair interaction, then bond pair interaction. So this interaction here, this repulsion here is the strongest interaction, right? Then these interactions off the side here, the second strongest interactions, right? And then we're gonna have this interaction here, the weakest interaction, right? So because of that dynamic, right, the lone pair interactions being much more stronger, lone pairs repel more strongly than bonded pairs. It's going to be pushing the bonded pairs into that angle, right? It's going to be pushing them down. Are you understanding what I'm saying? The persons who had issues.
Yes, sir.
All right, so it makes sense so far, so far. So it's going to be pushing
Yes,
them
yes,
into
sir,
that
that makes
structure.
sense.
All right, it pushes them in an angle. Fortunately for us as chemists, right, we have to know all these angles. For water, water is a bit different because water tends to be water. I don't know. Water is just different. All right, in every single case possible, water is different. Right, not only can it exist in all states at one temperature, but it tends to form a less dense solid and it tends to have a different bond angle. All right, can anybody just remind me of the bond angle of water? What is bond angle? Bond angle of water. You guys, it's in biology already, Unit
Is
1
it
biology.
104.5?
Wonderful. 104.5 degrees. Right, so that is the bond angle of water. But for general bent compounds, right, we call this a bent geometry. It's bent, or we call it V shape. So it has that bent geometry because it looks as if you held the hydrogen bonds and you just bend it, right? So it has that type of geometry, right? Molecules that tend to have a bent geometry tend to have a specific bond angle. We're going to be looking at that, and the fact that hydrogen bonded with oxygen in water tend to create this smaller bond angle than usual, right? We should be ending in the next hour, right? So we're gonna have this structure here. Now, what this diagram is entailing is that if we were supposed to submerge water in an acid, which we already know we're going to create an hydronium ion, right? Really, really simple stuff. We're gonna create a hydronium ion. What tends to happen is that water itself, just explaining this because somebody asked the question, right? So we're gonna have water itself having this structure, right? So we're going to be having no. Mm-mm-mm. We're going to be having this general structure, right? In which we're going to have one lone pair remaining on the molecule. And this lone pair is still going to exert a force on all other bonded pairs, pushing them down, right? So we're going to have a distortion. So it's not that, okay, one lone pair is gone because it's bonded. No, it's going to be flat. No, it's not going to be. Because we're going to still have that lone pair repulsion, right? Making sure that this geometry now becomes trigonal planar. Well, not trigonal planar, trigonal pyramidal, right? With bond angles of generally 107, right? Point something. But we're gonna be looking at these, right? We're gonna be having a look at these. So I just wanted to explain like what these are, right? Just explain what these are, how it looks, right? Water has a different bond angle for each of its structures, right? Generally, we're not gonna really explain why it has that, all right? But we're gonna have to know that it does, all right? And then we have ammonia down here that tends to have the correct bond angle. So 107.9 for that structure, and then 109.5 for tetrahedral structures, right? And we're gonna get into it though, all right? But are there any questions here though?
No.
No, sir.
All right, give me a second. Can anybody here visualize it properly? I want to make sure you guys can visualize it. Just let me know if you have an issue with visualizing it, and I'll see if I can attend to that issue. All right, I'm not hearing anybody saying that they have an issue visualizing these. All right, so let's just move on. So we are going to be predicting these shapes. Now, a VSEP number, right? So we tend to have this, right? So the VSEP number of a molecule is a number that describes the shape of the molecule, all right? So when we talk about the number, we're generally talking about the sum of lone pairs and bonded pairs in a molecule, right? This is a really, really, really simple way of looking at it, right? Really, really simple way of looking at the geometry. But I want to make sure that you guys completely understand the geometry. So we're going to be looking at a more advanced table after we go through each of the structures individually, right? So let's start with the first one, the most simple one, right? Linear shaped molecules, right? Now, a molecule has a linear shape, meaning line, linear, right? A very straight shape, right? If it tends to have two bonded species, right? So two bonds, right? But no lone pairs. So two bonds, right? And no lone pairs, no LPs. So it tends to have that straight geometry. And an example is beryllium difluoride, right? So beryllium difluoride is a wonderful example there. So it tends to be linear. We're going to be looking at them. I want to show you guys a simulation of these molecules, right? We have a trigonal planar molecule, right? When we have three bonded pairs. So we have three bonded pairs, right? And no lone pairs. Three bonded pairs, no lone pairs. So we have this type of structure, right? For example, this structure can be exhibited by our boron trifluoride that we looked at before. So boron trifluoride tends to have this structure with the fluoride surrounding, right? So it's gonna have this structure. Not sure why that is acting up, but yeah. So that is the general structure for trigonal planar molecules, right? If we have tetrahedral molecules, right, this tends to happen when we have four bonded pairs and no lone pairs, right? The information is on the slide, by the way, just going through it. So all of the electrons participate in bonding, and we have four bonded pairs around it, right? So four species surrounding a central atom. We have the tetrahedral shape, such as in the methane molecule, right? So we have that like that. We tend to have a structure that is trigonal bipyramidal when we have five molecules attached to a central carbon. For example, in phosphorus, pentafluoride, right? So that is another one there. And we tend to have an octahedral shape when we have six different atoms surrounding the central atom, as in sulfur hexafluoride, right? And so sulfur in this case would have an expanded octet because it can accommodate more electrons than 8 electrons, right? Because in this case it's accommodating, right, 8, 9, 10, 11, 12 electrons, right, around its center on its valence shell. So this is just a little bit of an introduction to the fact that the maximum number of electrons on a shell is not 8. It goes past the number 20. I think it even goes past the number 30, right? So things do happen, right? So this is an example of a molecule containing an expanded octet, right? So if there are any questions about that or any examples must be given, this is a wonderful example, all right? Are there any questions so far?
No, sir.
No.
No.
All right. So this is a general table that we look at for that I look at for geometries, right? So it's good to memorize the table if you would like to, right? E shows the central atom, X shows peripheral atoms, right? So atoms that are bonded to the central atom. And here we can know the different geometries generally, right? So if there are two electrons but no lone pairs, that would be linear, right? If we have two electrons and if we have three electrons and no lone pair, that is trigonal planar. But if we have three electrons, but we tend to have a lone pair, right? Then we're going to have a different structure. We're going to have trigonal pyramidal, right? So we generally have to look at stuff like this, right? We have to really look at it to understand the different structures. So this table is really good, and I do recommend that you guys understand the table, look at it a little bit, and play around with different structures, right? Also, the wedge system, the wedge hash system of molecular representation is important for us to understand before we go on to crystalline solids, right? I'm going to need hopefully a little bit more time. Okay, if I don't complete the PowerPoint in time, right, Then crystalline solids is really small, and all the information for crystalline solids is on the slide. So I'll just send it to you guys, and if you have any questions, you just ask me in the group, right? Just in case I don't finish that, right? But the wedge and hash model, right, of electronic representation, right? We generally have something like this. What structure would this be? This would be the Lewis structure of water, right? General Lewis structure. Um, I think water is a bad example. Let's use probably ammonia. Let's use ammonia as an example. All right. So we have ammonia here. Lewis structure of ammonia would look like this. All right. Generally, it would look like this, and then we'd have a lone pair like this, right? Based on valence selection, pair repulsion theory, where we have four bonded species. Well, we don't have four bonded species. We have four electron species, right? Four things surrounding the nitrogen. We have one, two, three, four things surrounding the nitrogen, right? Three of them are bonded and one of them are not, right? Based on the table here, right? We have four things surrounding, three of them are bonding and one of them are not. So we're going to gain trigonal pyramidal geometry, right? So we end up with nitrogen, right? It generally just looks like a pyramid, right? So that's it, right? So we're gonna have a nitrogen and we're gonna have one hydrogen within the plane, right? So within, if you're writing this down on a paper or anything like that, that's gonna be within the plane of the molecule, right? Then we're gonna have one of them coming out towards us. That is what we use the wedge for, right? And then we're gonna have one of them going behind into the plane of the page, which is the one behind. And then we have that lone pair there. So the blocked in edges, right, would represent anything coming towards you. The hashes mean anything going away from you, right? So that's how we represent the three-dimensional molecules on a two-dimensional plane, right? But before, I think I'm gonna end generally here, all right? But I want to look at the molecules in a three-dimensional way before we move on, before we just end. So give me one moment for me to launch the program so we can have a look at some of the geometries that we've been speaking about. All right. Are there any questions though before we move on? Before we just look at the geometries and then call it an evening?
No.
All right. So just give it a second.